Okay, gentlemen, we're coming up on it. We got 2 more weeks left after this Friday. Uh, so, you know, we're getting towards the end. We will not have some kind of all-encompassing test at the end of the year this year. We're just going to have our units. I may do one more quiz. You'll know ahead of time, but we're just going to go through our units kind of like regular, and where we end, we end. So today, I wanted to hopefully very quickly cover colligative properties. So we've talked about solutions and how things dissolve and how they interact with the solvent particles a little bit. And so what we're going to talk about today is colligative properties. And colligative properties are properties of solutions that depend on the number of dissolved particles and not their chemical identity. So it doesn't matter what chemical you put in the solution, it's going to change these three properties when comparing it back to the pure solvent. And you can think of the pure solvent in this case as water, because again, that's mostly what we work with, and it's just a helpful reference point. So when you dissolve things in water, three things happen to that water. The freezing point of the water is depressed, so freezing point depression. And it doesn't matter what you dissolve, just how many particles you dissolve in that water. So if you dissolve 100 particles of sugar, or 100 particles of salt, that would have the same effect on freezing point depression. By the way, freezing point depression is why we put salt on the roads, to melt the ice. It causes the ice to stay, well, the water, excuse me, to stay liquid down to a lower temperature, causing there to be less ice on the road, which presumably causes there to be, less accidents and stuff. The second property is boiling point elevation. So if you put, again, dissolve something in water, that water's boiling point is elevated. At standard pressure, it's elevated above the 100 degrees Celsius it would normally be. And then vapor pressure lowering, which is, of course, basically the pressure, or, well, it's basically how fast the thing dissolves. Vapor pressure is the pressure given off by the, not dissolves, excuse me, how it evaporates. It's the pressure given off by the evaporating vapor at the surface of a liquid. So any liquid should have, at anything other than absolute zero, would have some amount of evaporation occurring. Some particles are going fast enough, they hit the surface, and they're able to jump and become vapor. Because they're vapor, because they're a gas, now they give off pressure. So the vapor pressure is simply the pressure above a liquid from its vapor. And the more vapor it's making, the faster it's evaporating, the higher the vapor pressure. Well, you put a solute into some solution, let's say water again, or to some pure substance, say water, that solution is now going to have a lower vapor pressure. And we'll talk about why in a second. But again, these are the three colligative properties. You should know the definition and what the three colligative properties are. Also, any of you who take Latin should know what ligare, which is where colligative properties comes from. Ligare is also what gives us religion and ligament. So go look that up if you're so inclined. Okay, so here I have four, again, awesomely drawn cups containing half a liter, 500 milliliters of water. It's the same amount of water in each one. And I'm going to put into them 1 mole of these various substances. But it's not going to have the same effect, and there's a reason for that. So if I put in 1 mole of salt, sodium chloride, what happens is, and this is important to know and something we only kind of briefly discussed earlier in the year, what happens is the sodium chloride will break up into its component ions. Ionic compounds break up or dissociate into their component ions in solution. So 500 milliliters of water, you put in 1 mole of NaCl, you end up with 1 mole Na plus and 1 mole Cl minus for a total of 2 moles of solute. Solute particles, if you want to think about it that way. So because it dissociates, 1 mole of NaCl will, in fact, dissolve and create 2 moles of solute particles. We look at CaCl2, calcium chloride, metal plus a nonmetal, that's another ionic compound. It's going to dissociate into its component elements. But it's made of 3 component ions, right? It would dissociate into 1 mole of Ca plus 2 and 2 moles of Cl minus, because each one of those is made of a Ca plus 1 calcium cation plus 2 and 2 chloride anions, which are each minus 1. So 3 moles of solute over here. 1 mole of aluminum sulfate, which is a real thing that really is soluble in water. If I put 1 mole of aluminum sulfate, which is Al2SO43, into water, I'm going to end up with 2 moles of Al plus 3 aluminum cations, the 2 moles of aluminum cations, and 3 moles of SO4 minus 2, 3 moles of sulfate anions. Again, the ions separate, but sulfate, polyatomic anions, they stay together within themselves. They don't break apart. They're held together by molecular bonds or covalent bonds, so they don't break apart. So, with each of these, you notice the chemical formula has gotten bigger, so it kind of makes sense, or at least some people think it makes sense, that there's more, it has a greater effect. And this would, of course, be 5 moles of total solute. So let's go on to an even bigger chemical, sucrose, C12H22O11. And sugar, sucrose is regular table sugar, it definitely dissolves in water. So if we take that table sugar and we dissolve it in water, what we will get is 1 mole C12H22O11. So only 1 mole of solute. The reason for this, molecular compounds do not dissociate. They stay together. So ionic compounds, move this up here, ionic compounds dissociate into their component ions in solution. So 1 mole of salt actually makes 2 moles of solute. 1 mole of calcium chloride makes 3 moles of solute. So the salt has, a mole of salt has a bigger impact on freezing point depression than, say, a mole of sugar. So that's one of the reasons we don't use sugar on our roads. Calcium chloride, with its 3 moles of solute per mole of chemical, has an even bigger effect. And if you've ever seen the kind of higher capacity ice melt stuff, it's generally calcium chloride or some combination of sodium chloride and calcium chloride. Since calcium makes these 3 moles of solute, it has a bigger effect on water and depressing its freezing point than sodium chloride, which makes just 2 moles of solute. And of course, that assumes you put the same amount in each one. Something like aluminum sulfate would have an even bigger effect. The main reason we use salt, by the way, it's better than something, molecular, but it's cheap and easy to mine. And also right here in Cleveland, we live on a big salt mine. Under Lake Erie, there's a huge salt mine. So it's relatively inexpensive is part of the process. Calcium chloride a little bit more expensive, though it does work to lower temperatures because, again, it makes those 3 moles of solute. And of course, something like sugar, aside from being more expensive because you have to process it, it only makes 1 mole of solute per 1 mole of sugar particles. And also, this sugar particle weighs like 360 grams, whereas salt, sodium chloride, weighs like 58 grams per mole. So 58 grams of this has twice the effect as 360 grams approximately of sugar. So again, by weight, it also makes more sense to go with salt. So ionic compounds dissociate into their component ions, and so they have a bigger effect on colligative properties. Molecular compounds stay together in solution. It turns out acids and bases, and we've talked about acids and bases. Acids kind of are halfway. Some acids dissociate completely, some acids dissociate a little bit, some barely dissociate at all. And we'll get into that if we have time at the end of the year. But acids, again, kind of straddle that line between acting like ionic compounds and acting like molecular compounds. They're right in the middle of that. This whole thing is a continuum. There's not like one side is completely different than the other side. There's a whole continuum, a whole gradient where we have just drawn a line kind of to determine, to make our lives easier as far as classifying things. But there's things very close to that line which could be classified as either. So it's just, our line that we've drawn. Okay, so why do these things have these effects? And this will be the last slide, I believe. Yep, last slide. So it's pretty simple, at least at a very basic level. The reason they have their effects is when something dissolves in water, and we're just going to use water as our example solvent, it interacts with several of the water particles. And that interacting makes those water particles act a little differently because they're busy interacting with, say, water particles. So let's say this is just salt water. These purple uh, the purple, excuse me, dots represent salt, and the blue dots represent water, that the water particles that are interacting with that salt particle. They're actively dissolving it. Well, what happens is those particles, because they're interacting with salt, have a harder time breaking free and being able to evaporate or boil, depending on what the temperature is. And basically, the salt is kind of interacting with them and holding them back. So that means you need to put more energy into them for them to be able to boil. Or for if it's you're under the boiling temperature, what's going on is these particles are basically taken out of the group that could potentially evaporate. So since there's less particles that can potentially evaporate because these ones are busy interacting with salt particles, less particles do evaporate and the vapor pressure is lowered. And fire is indeed hot, by the way. I'm such a bad drawer or artist that I actually just labeled that because I figured you might not know what the heck was going on. So if you put salt in your pasta water, it actually makes it take slightly longer to boil because it has to get to a slightly higher temperature. Now, unless you're putting way too much salt in the pasta water, it's less than 1 degree Celsius. But it does actually raise the boiling point. Finally, for lowering the freezing point depression, which is one of the uses we see a lot because we here in Cleveland understand that they put salt on the road. What happens is when water freezes, or when anything freezes really, it slows down enough. Remember, freezing is just, well, cooling is just the particles moving less. It freezes when it slows down enough that the intermolecular forces can completely hold it together as a solid. And what happens when there's particles involved there, particles dissolved in it, is those particles kind of get in the way and act as a buffer and basically cause it to be harder for it to be held together by the intermolecular forces. Now, eventually, if you cool it enough, it will expel these purple particles. They'll all get pushed to the side, and it will make its solid crystalline structure in the form of water. But it makes it harder to do that. So you have to take even more energy away from the water, get it going even slower, because instead of just having to hold the water particles together, the intermolecular forces also have to deal with this buffering situation. So they have to get those water particles going even slower so that they can kind of push out or expel whatever the solute is so that they're able to then finally freeze. So freezing point depression, boiling point elevation. By the way, these two things, the freezing point depression and boiling point elevation, is why we use coolant in our cars, assuming you have a liquid-cooled car, basically a gas engine or a diesel engine, as opposed to, say, just cooling with water. We don't use just water to cool. We actually use what we call antifreeze or engine coolant, which is a solution. And that's why, because it both elevates the boiling point and depresses the freezing point. And it's very important that the cooling system the coolant stays liquid. Otherwise, it won't work to cool your system, your engine. Okay, so that's colligative properties. Know what they are, or at least, be familiar with what they are, familiar with their definition, and, didn't mean to hit that. And be familiar with the fact that ionic compounds will have a larger effect because they provide more solute particles than covalent compounds because they break up, and have some understanding of how the solute particles interactions with the solvent, in other words, the dissolved particles interactions with water in our examples, affects these properties, or why it affects these properties. Okay, 2 more weeks. Thermochemistry is up next. Have a good weekend, gentlemen.